Force, work, and energy review 16. A mass M is attached to a rod of negligible mass and length R. Now, later on in this series of videos, we will deal with the case where there's a rod here that has a macroscopic mass, and that is going to be a different case than what we're showing here. But here we're assuming that this rod's mass is completely negligible and that the only mass that's relevant is what we have here attached to the end. So we're going to drop this thing. We have a pin, let's say, right here, and this thing is going to swing down like that, and we want to know what its speed is right at that instant. So I think we should use conservation of mechanical energy. The initial energy is equal to the final energy. There are any number of ways you can do this, but the way I'm going to do it is I'm going to say, you know what, right along here, right there, that's going to be my reference line, which means H equals 0 right there. The mass at this point will have only kinetic energy. So E final is going to be 1/2 m V final squared. It will have no gravitational potential energy. But initially it does have gravitational potential energy equal to m times g times h. Now what's h? Well, h in this diagram is this distance right there. That's h. Based on the figure, what does that turn out to be? This r here, this dotted line, isn't that also r? Those are both r. So this h is equal to r sine 30. So let's change what we have written over here. Well, the masses can go away. So we're going to go g times r sine 30 is equal to 1/2 v final squared. Can we do the sine of 30 in our head? I think we can. The sine of 30 is actually 1/2. So the 1/2s cancel. There you go. In terms of the variables that are given, v final is going to be the acceleration due to gravity times r square rooted.